I'm going to talk to you right now about confidence intervals with limited data. So in this context, limited data means very few observations. So normally for the central limit theorem, we'll talk about having more than 30 observations. When I say limited data, I'm talking about we only have very few observations, like 2, 3, 4, 5, up to 10, 15, something like that. So few data points. So the central limit theorem says that x bar is approximately normal with mean mu and standard deviation sigma squared over n. We use this result, the central limit theorem, to derive a 95% confidence interval for mu, and we just take x bar plus or minus 1.96 times sigma divided by a square root of n. Usually we don't have sigma, so we kind of wave our hands and say, all right, that's about the same thing as x bar plus or minus 1.96 times s over square root of n, where s comes from the variance, where s squared is the sum of xi minus x bar squared divided by n minus 1. So that we just plug in the sample variance for the true variance and get this. And usually this works fine if we have enough data that s squared is close to the true sigma squared. But what happens if n is very small? So what happens to s squared if n is small? Suppose, for example, that n equals 2. Then s squared is equal to x1 minus x bar squared plus x2 minus x bar squared divided by 2 minus 1, which is just 1. So we get x1 minus x bar squared plus x squared minus x bar squared. That's it. Okay. So is this number accurate? Will it actually get us something like sigma squared? So you can test this for yourself in R. If you do ST for standard deviation, that will get you S in our book's notation. And R norm, this means 2 samples from normal 0, 1. Distribute. So the first one that I plugged in here, I got 0.14. The actual value should be 1. Instead of doing it just one time, I did it this same statistic 1,000 times. So the first one happened to be less than 1, which is the true value. But here's what the histogram looks like. Looks like this for this statistic. So the true value here is 1. This is what it should be. So the true value is equal to 1. The problem here is that S is not close to sigma. So on the x-axis here, these are all our S values that we're observing when we have 2 observations. And as we can see, this distribution, they're just not really that close to the true value of 1. So because this is the case, when we go to make a confidence interval using this formula here, because S is not a faithful representation of sigma, things don't work out as we wish they would. So that's why we need this alternative procedure that I'll talk about in the next video. That's the t-distribution. So we'll use that to account for this change in S, and I'll explain that.